is Philippe Van Kerm. I'm a professor of social inequality and social policy at the University of Luxembourg and at the Luxembourg Institute of Socioeconomic Research. In this short LISSY video tutorial, I'm going to show you how to use loose bootstrap replication weights in order to conduct your inference in loose-based analysis. Okay, so I'll be assuming that you already know what bootstrap inference is, but in a nutshell, the idea is really quite simple. Here is our data set, and we have, let's say, just 5 observations identified, 1, 2, 3, 4, 5. And let's say we've got some variable of interest, let's say household income, which is 3, whatever 3 means. We've got 3, 5, 3, 2, 1. Okay, and let's say we're interested in calculating some parameter of interest, theta, and an estimate of that will be calculated on that vector. Let's say it's the Gini coefficient. Alright, so this is some form of income, and we're interested in calculating the Gini coefficient for that vector. Alright, we've estimated that from our data set, and we now want to do some inference. We want to estimate standard errors, we want to estimate the confidence intervals around that value. So how do we do that? Well, the Bootstrap is offering one very simple solution to those estimations. So the idea of the Bootstrap is as follows. A new sample of size 5 drawn with replacement from that original sample. Okay, so for example, we're going to create our first Bootstrap replication here. Still 5 observations, but no, okay, we're going to do that randomly. That's our first Bootstrap sample. Let's re-estimate our Gini coefficient. Okay, we've got the new value for the Gini coefficient calculated here and call it value 1. Okay, let's repeat that. From which we calculate a new Gini coefficient. Okay, and we are going to repeat that a large number of times. Okay, so these are Bootstrap samples, so drawn with replacement from the original sample. And the idea of Bootstrap inference is to actually use those replicated value, so the distribution of those replicated value, to make inference about the sampling variability of our original estimate. So for example, we're going to use the standard deviation of the Bootstrap replication here as an estimator for the standard error of our original estimate. Okay, as simple as that. And from that distribution, we can also calculate confidence intervals, we can also derive statistical tests, etc., etc. Alright, so that's the idea. Now, Bootstrap replication weights. So what are Bootstrap replication weights? Well, these are simply a convenient way to store our Bootstrap samples. So the idea is that, okay, we've seen those replications here. We could have written them as follows. So that's just an equivalent way to actually write our Bootstrap samples, and we can still estimate our Gini coefficients on each of those new data sets. Okay, but now we're simply going to use a weighted estimator of the Gini coefficient, where we use the Bootstrap weights here as weight in the calculation. Now, those two variables are always the same, so you don't want to store them separately in all sort of replications. What you can do is actually just calculate all those replication weights and put them in one big file. And that's 999 replication weights. So that's exactly, that file here, that I've described here, is exactly what the loose replication weight dataset contains. So 999 replication weights. It also contains household identifier and the data identifier, which you're going to use, which is the key that you're going to use to map onto the household level or personal level datasets. Okay, so that's the idea. That's what the loose bootstrap replication weights contain. Okay, I've oversimplified things here. And what have I oversimplified is that in fact those bootstrap replication weights can be used to actually reflect the survey design. And as you know, those the surveys that are stored in the loose have complex survey design. They involve stratification. They often have multi-stage design. The weights are also typically calibrated, and there's post-stratification applied. So all of that and has been in loose incorporated in the construction of the replication weight. So what you're going to see in loose, if you look into the data, are not just like integer numbers here. There are going to be numbers which are going to be missing when it's simply 0, and they're going to be essentially sampling weights. But they use the way to use it and the way to derive the standard errors for the theta, for the parameter of interest, is just exactly the same. Okay, so I think I've said all that needs to be said. Let's just look at a few examples how to actually incorporate that in our analysis on LISSY. And, well, follow me there. Now let's look at an example on LISSY. So I've selected the loose dataset, selected Stata. I mean, my example is in Stata. You can work with other statistical packages. Obviously, the calculations are fairly simple. And whatever subject, bootstrap replication weight examples. Okay, let's load some examples which you'll be able to download from the LISSY Data Center website. Okay, let's go and let's look at the first example here. Alright, use replication weights and multiple imputations. So in this first example, let's just discard. We're firing the US SCA for 2016 using the household level data. Let's do a very simple exercise. And we just load a few variables. Okay, keep inum equal to 1, so keep only one implicate data. Very important not to work with all of them if you don't properly take multiple imputations into account. Okay, keep if inum is equal to 1. Merging in, so it's a one-to-one merge on the household identifier with the file which holds all the replication weight variables. Okay, so we'll look at how those variables look like. Now, the key thing here in Stata is to declare the survey characteristics. So I'm typing SVY set, telling that the sampling weight is variable HPOPWGT. PSUHID, that's not actually going to be used for the bootstrap replications, and we're going to see an example of what difference it makes. That's the key line. That's where you declare the bootstrap replication weights. You just use this option, BSR weight, and list all the variables which contain the replication weights. So notice that I've stopped here at 99, so I've only used the first 99, just in the interest of speed in this example. Obviously, in any serious application, you will want to use the full 999 replications. But I'm telling Stata that, again, by default, when SVY is being called, I want default standard errors calculated using linear standard errors, just in interest of speed, and I will only use replication weight when I call SVY bootstrap. Alright, so SVY mean A and W is going to calculate the average adjusted net worth in the data and the standard errors and confidence intervals using the survey characteristics. By default, it's using linearized calculation of standard errors, but I can also get this inference being done using the bootstrap replication weight by specifying survey bootstrap as a prefix and then the command I want to get the inference for. That syntax will run for any stata command that accepts the SVY prefix, which is pretty much all of the estimation commands. And there's also some user-written command, like this one inequally, for calculating inequality measures. That's described elsewhere. And what's actually quite useful with SVY Bootstrap is that it also runs with non-E-class commands. So you can do inference with commands that don't actually normally report standard errors or confidence intervals. So here's an example with the package, again, another user-written command sgini for calculating what sgini coefficients. Sgini normally does not report any standard errors. It only reports a point estimate. But here you can get the full inference using the bootstrap replication weight by specifying, again, SVY bootstrap. Now here, because it's not storing its estimates in EB instead, but the key coefficient is stored in RCoef, we have to tell it that this is the coefficient that we want to retrieve from that command and calculate the standard errors for. So here's the syntax, SVY bootstrap, Gini is the name I'm giving to that coefficient which is being calculated here. And stata is going to use the bootstrap replication weight to calculate confidence intervals for SGs. Okay, not all R-class or user-return command would accept the SVY prefix. This is a property of the package. If you're trying to use a command which does not accept the SVY prefix by default, well, you'll have to tweak your code a little bit using something like this. You'll have to define a program. So program define, give it whatever name. So here we're going to use summarize to calculate the coefficient of variation with standard errors. So say program define. It's going to be an R class for simplicity, and the important parameter is the option properties SVYB for survey bootstrap. Now here the little tweak is to actually transform any input PW, which is not accepted by summarize, into an IW, an I weight. For point estimation, provided the weights are positive, that's not going to make any difference. So that's the syntax. Okay, I'm not going to spend much time onto it. You can study it for yourself. And then I just call summarize whatever is the user input. And from summarize, calculate the coefficient of variation. So it's the standard deviation divided by 2. And I will actually also retain the mean from summarize. Having defined this, I can now call my new program COV, coefficient of variation, on adjusted net worth, and prefix that command with SVY bootstrap, and tell instead that I want to recover here both the coefficient of variation and the mean. And this is it. The output of that is going to be the coefficient of variation, the mean with inference. Once this is done, you could use all post-estimation commands of stata, you can run tests and things like that. Sometimes that's a silly example that I'm showing you here. But once the standard errors are calculating using the SVY bootstrap prefix, you can use all the post-estimation statistics that are typically available. There we are. So let's just run that and see what we get. So here we are, our listing, our text. Alright, let's look at the output now. Well, as you're going to see, it's going to be really very simple. Use, we merge on HID after having kept only one of the implicates. We've got all observations matched 1 to 1. We now can look at the output. Right? So the summarize of all the weight variables. So as you see, in the replication weights, the number of observations is less than the full, so not all observations are being used. So that's the non-drawn observations. They receive a weight actually of 0 or of missing in this case. So this only counts the observations which have a non-zero or non-missing weight. So there's obviously a little less than the full sample. And of course then, because these store sampling weights, well, the sampling weights, when the sample size is a little lower, the sampling weights are larger. There's a bit of variation here. And as you see, the range of variation of those sampling weights, or the replication weight, is sort of similar to the range of variation that you observe in the sampling weights. Okay? And then we do all the declarations here. There's nothing interesting to look at. So the only thing we want to see is that actually what you get is very similar. That's the output. And it's important to realize that actually those would be more reliable, because the replication weight actually incorporate, as I've said, complex survey design characteristics, in particular stratification, which tends to reduce the standard errors of the estimates. And this also takes into account, for example, the oversampling of the wealthy, which is being done in the survey of consumer finance. While the estimate that we could do when using the linear standard errors, because we don't have all that detailed information on the sampling design in the data, this is likely incorrect. And as we see in this example, we've got bootstrap standard errors which are much, much lower than the linear standard errors, which suggests that adjustment for the complex survey design would be very important. And actually, this also suggests that not taking those into account actually leads to much larger confidence intervals than if we take those into account. So these would be the more appropriate estimates of the standard errors for the average net worth. Okay, Gini coefficient, that's exactly the same. Once you've declared the data to survey bootstrap weight, it's taken into account automatically. We also see that the standard errors are much lower if we use the replication weights than if we do standard basic linear standard errors that don't take into account the full sampling design. And confidence intervals as you have with inequally. So you see the inference is exactly the same, although it's derived from two different commands, one E-class, one non-E-class. And then here we've got the example using this little wrapper command to allow any user-written calculations here flexibly. And as you see, we now have bootstrap standard errors, confidence intervals for the coefficient of variation, even though there's no command off the shelf to actually calculate that. Let's now look at a second example. So in this second example, we're going to use the replication weight to compare the evolution across 2 different years, here in this example for the US. Okay, so how do we do that? Well, what we're going to do, we're going to start by stacking 2 different years of data on top of each other. So we're using the 2016 data for the US, as we did before, and we're going then to append the data set for 2010. As before, we only work with the first implicate, so we keep if INM is equal to 1, which is going to keep only the first implicate in the 2 years. Then we merge in, again, it's a 1-to-1 match, but now we're using the dataset identifier and the household identifier to do this 1-to-1 match with the replication weight for 2016, and we repeat that with the replication weights for 2010. Here we are using the update option to replace the missing values in the existing replication weight variable which have been loaded for 2016. So now the replication weight are going to contain replication weights for each of the 2 years separately. Alright, then survey set the data, again same sampling weight. Now the only variation here is that we are declaring the year variable to be a stratification variable. Effectively is telling its data that these two, the data coming from the 2 years, are actually samples which have been drawn independently from each other. Okay. And we are considering here with that little strategy here is that the 2 different years are actually 2 different populations that are being sampled from. Sampling weights as before, LISSY linearized as default, this is as before. Now, survey bootstrap prefix. The only difference from the previous example is that now we are specifying which year we want to have an estimate from. So there's two strategies which would be equivalent in this particular example, either to specify subpop, with the subpop option, the condition year 2016 or year 2010. In this specific example, this would be equivalent to specifying the if year condition just after in the comment as before. That would be equivalent in this particular example. Okay. Now imagine we wanted to test for the difference in the estimates across the 2 years. Now that's going to be a little more complicated because we'll need to write a small wrapper program which is going to do the calculation for each of the 2 years. So in this particular example, calculating the Gini coefficient for 2016, the Gini coefficient for 2010, and returning the difference between the two estimates. Okay, that's the purpose of this small program. And as before, well, it's important to set the properties of this program as SVYB, so that it accepts the survey bootstrap prefix, and we use an rclass command. Okay, don't worry too much about the first part here. The idea here is that we are passing the input which is going to be automatically generated by the survey command, survey prefix. Okay, so a small wrapper program, and the idea is simply to calculate the two measures and store the difference. Having done that, survey bootstrap prefix, telling that we want to keep this diff result as a statistic being bootstrapped, there it is, and then dgini run again is a little trick. You don't have to worry about that. Any word would. That is actually going to use the replication weight to calculate the inference, the standard errors, and confidence intervals for the difference between the Gini coefficient in the 2 years. Okay, now let's look at a different way to do that same sort of calculation. I think it's useful to also see how to do those calculations entirely manually. So in some cases, you may want to do these calculations manually. And it's all really easy. Look at this. So let's first calculate the point estimate. So SGini calculates the Gini coefficient in 2016, storing it here, calculating the Gini coefficient for 2010, and we're saving the value for 2010, and we are saving the difference between the two, which is the statistic we want to have some confidence interval. Okay, so let's now do the bootstrap by hand. Well, it's not very complicated. So we are going to loop across all, well, only here 99 again. Remember, you should do the full 999 here. But in this particular example, let's do it only for 99 replications. So we're simply going to loop across 99 replication weight variables, and all the rest is going to be just as before. The only thing that varies within the loop is the specification of the weight. Right? All the rest is the same. And the only thing that we do here additionally is calculating the standard deviation of the estimate of the difference across the 99 values. So what this does is actually updating the difference, the standard deviation as we go. There's nothing else than this. Okay, so we just look at the squared deviation of the observed difference in the loop with the original difference calculated in the full sample. Okay, so once data has done this 99 re-estimation of the two values and the difference thereof, take the square root of the variance, already this was the variance of the standard deviation. So we've got an estimate of the standard error, which is the square root of this difference here. And we can also construct normal confidence intervals, upper and lower bound, 95% confidence interval, by taking normality assumption. So we're simply using the point estimate plus or minus 1.96 times the estimate of the standard error as estimates for the upper and lower. And that's only displaying the results. So let's run that and see what we get. Okay, so what have we got here? So we have two one-to-one match, which work, values updated. We then have the 99 replication weights, and there we go. Estimates for 2016, point estimate confidence interval, and we've got the estimate for 2010. So we see there was an increase in the point estimate of the Gini coefficient for adjusted net worth, and we see that apparently the increase, albeit seemingly small, is actually potentially significant, as we see the confidence intervals that we get are fairly narrow and they don't overlap. Of course, we want to do a formal test of that, so we're going to look at the confidence interval for the difference between the two. Okay, so here is using our little wrapper program, the estimate of the difference that we get from Survey Bootstrap, and we see, so the difference, the increase has been of 0.013, and we see that the confidence interval indeed do not cover 0, so that apparently the increase in inequality is statistically significant. Okay, what do we get if we do that manually? Okay, this is our loop, and this is the outcome that we get by doing the estimations manually. So just I repeat the estimation here so we can easily compare. And as you can see, we've got exactly the same point estimate of the change, and we've got the same up to rounding values for the confidence intervals for the change. So you see, two different ways to actually calculate the bootstrap standard errors of the change in our estimate. Well, in our third example, we're going to combine replication weights and multiple imputations. So I've already shown you this example in a video on using multiple imputations with LU, so I recommend you look into that video first before trying to understand this example. But here I'm just going to quickly show you that the replication weights can be combined with the multiple imputations. So in the first part of the example here, this is the syntax that I show in this other video on multiple imputations, showing you how to actually declare data to be multiply imputed in Stata, including the creation of a version 0, imputation 0, which does not contain any of the, contains missing instead of imputed values here. Okay, this is the multiple imputation stage. And further down here, we have the variation to the declaration of the bootstrap replication weights here to allow for multiple imputation. So now notice that we haven't discarded all but one implicate. We keep all implicates, declare the data to be multiply imputed. We convert the format to a wide one so that the multiple imputations are in different variables, not stacked on top of each other. Doing then a one-to-one merge with the replication files. And now the only difference is, so we know MI survey set the data, so MI survey set, weight variable, bootstrap replication weights, VC linearized, all that just as before. And now we simply need to combine the two prefixes, survey bootstrap, with the MI estimate prefix to apply the multiple imputation, to handle multiple imputation in the estimation. There's this little trick that we need to use VCE OK in that when we specify survey bootstrap and MI estimate, but once you know it for good. So what we get here is MI estimate VCE OK, survey bootstrap mean AW or inequally are estimates of the average adjusted net worth or the Gini coefficient of adjusted net worth, where the standard errors and confidence interval estimate will take into account the inference based on survey bootstraps, on the variance in the estimates that's driven by the multiple imputation. So what have we got when we run this third example? Well, first we have the full 5 implicates rather than keeping only one in the previous examples. Now I'm skipping this part that describes the creation of the empty implicate, that describes specifying the multiple imputed data into stata. And I'm jumping to that stage where we simply merge in the multiple imputed data the replication weights. It's a one-to-one merge because we have converted the stacked observations into a wide format. We now use mi_svy set instead of svy set, declaring the replication weights as before. And that's all we need to do. Now we can run mi estimate, BCE OK, survey bootstrap, mean adjusted net worth, and we've got an estimate. The mean adjusted net worth and the corresponding standard error and confidence interval. And those estimates actually take into account both the variability that's due to the imputation error, so that's the variability of imputation across implicates, and the variability within implicates. That's the one that's being picked up by the replication weight, and that's the more standard source of standard error. And finally, this exact same syntax, but now using inequally to actually calculate the Gini coefficient, and we have an estimate of the Gini coefficient and the corresponding standard error and confidence interval, but one which again takes into account the variability which comes from imputation of missing value and from the standard replication weights. That's it. I hope this video tutorial was useful.